Okay, and welcome to lecture 16, parte dos. We are still continuing talking about different kinds of reactions, and today we're going to talk about acids and bases. Okay. A good definition, one that covers the majority of acids, is that they donate an acidic proton, okay, an H+. So for example, HCl, you drop it in water, breaks up into H+, and Cl-. Vinegar or acetic acid breaks up into H+ and acetate. This doesn't cover all the acids, but it covers most of the acids we're going to work with. Base is pretty much the exact opposite. It is what accepts a proton. So, for example, HCl acting as an acid will react with ammonia. That will give you ammonium, the polyatomic ion, and chloride. Okay? So ammonia is acting as a base there. It's accepting the acidic proton. Similarly, you have sodium hydroxide or lye. You drop it in water, it's going to break up into Na+ and OH-. Okay. It's the OH- that's acting as the base because H+ plus OH- makes H2O. To be perfectly honest, perfectly truthful, that's not precisely how acids and bases work. What really happens is that there's always an acid and a base acting together. The acid is an acid because it's donating a proton to a base. Okay? And most of the time, that base is water. So what you're really getting when you drop HCl into water is this reaction. The water is accepting the acidic proton to become hydronium. And that is what you actually find floating around in solution. You don't have the naked protons flying around quite so much. Instead, you have hydronium. Likewise, you don't really have a base except when it interacts with an acid. And a lot of the time, that acid is water. Yes, water is both an acid and a base. Okay. It's an amphoteric substance. Okay. An amphoteric substance is anything that can act as an acid or a base. So in this case, water is donating an acidic proton to ammonia to make ammonium and hydroxide. You do get hydroxides floating around in solution. You don't get hydrogen proton or hydrogen ions floating around by themselves in solution. So in any event, this is water acting as an acid because it's donating the proton to ammonia. And up here, up top, it's acting as a base because it's accepting a proton from chloride. And water can act all on its own. You get water plus water making H3O plus and OH-. Even in neutral solution, it will do this. So one of them will be acting as an acid, the other one will be acting as a base. This one of them is donating a proton to the other. To make, just to reiterate, hydronium and hydroxide. Now, this isn't a huge portion of water. It's in fact a very small fraction, but it's always there. Now, real quick, let's talk about strong acids versus weak acids. A strong acid is anything that 100% ionizes in solution. Okay. So when you throw hydrochloric acid into solution, HCl goes to H plus Cl minus. That happens 100%. Every single hydrogen chloride molecule breaks apart into H plus and Cl minus, or technically hydronium and Cl minus. There are 7 strong acids. Okay? HCl, HClO3, HClO4, HI, HBr, H2SO4, and HNO3. Hopefully you recall the names of those from learning about ionic and acidic nomenclature. Hydrochloric acid, hydroiodic acid, hydrobromic acid, chloric acid, perchloric acid, sulfuric acid, and nitric acid. Those are the 7 strong acids. Now, weak acids, hopefully you can guess by contrast, they are less than 100%. Okay, so something like acetic acid, HC2H3O2, you throw that into solution, it breaks apart into H plus and Cl minus. That's something like, it's not particularly clear, that's something like 4%. Okay, so way, way less. And anything that's not a strong acid, if it's an acid at all, I should say, any acid that's not a strong acid is a weak acid. It's going to have less than 100% ionization. That's the definition I want you to focus on. In a similar vein, we have strong bases versus weak bases. The definition is pretty much exactly the same, except that a lot of bases are ionic, so this would be 100% ionization or dissociation, and this is less than 100%. So the strong bases are the alkali hydroxides. So that would be, sodium hydroxide, potassium hydroxide, etc. Let's go ahead and put ... because those aren't the only 2. And the heavy alkaline earth hydroxides. Okay. So those are barium hydroxide, calcium hydroxide, and strontium hydroxide. And those are all of your strong bases. Okay? So really, ionization doesn't come into it, it's just dissociation. They're all perfectly soluble in water. Okay? So they break up 100%. Okay? The weak bases are any other metal hydroxide and any molecular base. So when I say molecular base, I mean any covalent compound that acts as a base. Okay? So that would be, say, ammonia, NH3, or any amine. An amine is a carbon compound, so an organic compound, say methylamine, so H3C and H2, or ethylamine, H3C, H2C, and H2, and so on. You see they have nitrogens on there, and the nitrogen has a non-bonding pair that will bond with H+. Anywho, you also have a class known as amides, which likewise have a nitrogen on them. Nitrogen is big on acting like a base when it's in a covalent compound. Doesn't always, but a lot of the time. So any molecular compound that acts as a base is going to be a weak base. So it's less than 100% ionization. I just wanted to introduce those to you. Go ahead and get them out of the way. We'll be discussing, or you will learn about acids and bases in far more detail when you get to later chemistry. For now, we'll just leave it at that. And we'll go ahead and talk about the reactions we came here to talk about. Now that we know a bit more about acids and bases, we're going to talk about neutralization reactions. A neutralization reaction is any reaction acid plus base. Okay? So anytime you mix an acid and a base, they're going to react, they're going to neutralize one another. Okay? They're going to react to form usually water and a salt. Okay? It's always going to form a salt. Depends on the acid and base in question. And it usually forms water. Again, depending on the acid and the base. So, for example, you could react H2SO4 with calcium hydroxide. Okay, this is a strong acid with a strong base. And what you're going to get is calcium sulfate, that's your salt, plus 2 H2O. Okay, because H plus OH minus yields H2O. Okay, so there's water. Now, like I said, you don't always get water. For example, hydrochloric acid plus ammonia, that's a strong acid and a weak base. That's going to make NH4Cl, ammonium chloride. That's it, no water. Okay, the important thing to note here is that we have strong acid, strong base, strong acid, weak base. Neutralization reactions ignore that distinction. You should not. Okay, you should remember strong and weak acids and bases because they'll be fairly important moving forward. But the neutralization reaction itself doesn't pay too much attention to strong versus weak. You're just going to get your salt and possibly water. Okay. So what you need to do is you need to learn to recognize your acids and your bases. Okay. The strong acids, you really do just have to memorize those and learn to recognize your acidic protons. When you see an H written out front without necessarily having any good reason for that, it's usually an acidic proton. You should recognize the OH minus, the hydroxide, easily enough. The more difficult weak bases are going to be things like ammonia. So once again, you're just going to have to learn that. You're going to have to memorize. And I recommend you do so. Okay. But that is neutralization reactions. Those are quite a bit easier than those precipitation reactions. Quite a bit less to memorize. Quite a bit less to worry about, try to recognize. No complicated solubility rules. But they are a fairly important class of reactions. Acids and bases show up everywhere in biology, especially for those who are going into biochem or medicine. Acids and bases are vitally important to life. But that's it for this lesson, or this part of the lecture, I should say. When we return, we'll talk about oxidation-reduction reactions.